And now let me see how this goes. Okay, so this is where we were, right? Yep.
For the hexose transport, how it was like glucose and galactose go together and then fructose, would those happen simultaneously or is there different timing for like when fructose?
No, those are kind of independent. So,
Whenever they're there.
yeah, whenever they're present, both of those transport systems could be working.
And glucose and galactose can go in like one at a time. They don't need both of them to be linked.
Correct. Two sodium ions bind, and then either galactose or glucose.
But sodium has to be kept differently.
Yeah, that's what kind of switches on that transporter. Sodium binds, structure shifts. It'll bind either glucose or galactose. They go in, then repeat. Yep, that's obviously something good to know. So go through that process, okay? And that has applications every day about how fructose is slower than the other two, and so that's something that you'll use that kind of as background information in upcoming classes as well. So we're kind of tracking, especially glucose, as we go through this process. And we've said, for example, that glucose goes in the portal vein. Once it's in the portal vein, we looked at distribution. We know that quite a bit of it does go in the liver. And we said that it goes into the liver cells mostly through GLUT2. We talked about the characteristics of that. We also talked about how when we're not consuming carbohydrate and blood glucose drops, how the liver can contribute glucose to the blood. And in those cases, it's either through glycogenolysis or gluconeogenesis, but GLUT2 can also participate in that process. One of the things we said was, when glucose goes in, it's converted to glucose 6-phosphate. Glucose 6-phosphate is not substrate for GLUT2. So if glucose goes in and is converted to glucose 6, it's essentially trapped. You heard that term before, metabolic trapping? That means a metabolite or a metabolic reaction converts a molecule to either keep it inside the cell or outside the cell or an organelle or something. In this case, we're going to talk about the enzyme that does that in different tissues. So that's what's here. Same slide, but now we're going to focus on a different part of it, right? This requires ATP. So this is energy dependent, and you probably remember that's the first step of glycolysis, where it goes glucose to glucose 6-phosphate. So we're investing some energy here, and we're trapping glucose inside this cell. And the enzymes that do that add phosphates, are called kinases. So these two kinases, hexokinase and glucokinase, do the same reaction. But they're what are called isoforms. Right, they're very similar proteins. These do the same reaction, but we're going to talk about characteristics of each different form of the enzyme and how it's advantageous or a disadvantage. So here's glucose to glucose 6-phosphate. So if I ask you to write this out, it's fair for me to say, you got to write the structure of this. You got to write the structure of this. And you can just cheat this way. Just go oxygen phosphate here. You don't have to draw the other oxygens. We're going to say this is hexokinase. This is glucokinase. So there's a couple different things about these enzymes. One is their tissue distribution. In other words, where they're expressed. We're going to say glucokinase is expressed in liver cells and beta cells. Liver cells and beta cells. Hexokinase, pretty much everywhere else. So we'll say extrahepatic tissues. I'll give you a couple reasons why it makes sense for them to have two different forms and them to be distributed in different tissues. One is hexokinase. I think I have this here. I should. Hexokinase has a high Km. Sorry, did I say hexokinase?
Yeah.
Glucokinase has a high Km. Hexokinase has a low Km. So which enzyme's faster? Glucokinase. High Km is high capacity. So high Km is faster, just remember that. Okay. So the low Km is slower. We'll talk about why. We'll talk about some enzyme kinetics a little bit later. So far that's what we remember. So now the other thing that's unique about these enzymes is hexokinase is regulated by this product. What do we call that? And we say,
Product inhibition.
yeah, product inhibition, negative feedback, anything like that. Basically, its activity is slowed down by the product. Okay. Now let's look at this and why that could make a significant difference. Now remember, the only tissue in our body that will contribute glucose to the blood to help maintain blood glucose is the liver. So postprandial, it's advantageous that the liver can take up a lot of glucose and store it. So in this case, as it goes into the liver, glucokinase can phosphorylate a lot of glucose and trap it in liver cells. And in that case, it's okay, because if later on it needs to give that glucose back, it can. So the liver can absorb and phosphorylate a lot of glucose. It can phosphorylate it because glucokinase has a high Km. It can absorb it because GLUT2 has a high Km. So in this case, this is another example of if it makes sense that the body should do it this way, that's the way it works. Our body has kind of paired a fast kinase with a fast transporter. So GLUT2 has a high Km, and so does glucokinase. The reason those are also involved in beta cells is because beta cells use high glucose to release insulin. Sure. So beta cells also have glucokinase and GLUT2 so that they can absorb and phosphorylate significant amounts of glucose, because they use glucose to release insulin. So that makes sense, right? Like after you eat a meal, a lot of it can go into the beta cells. It's phosphorylated, it's metabolized, and that metabolism, we talked about this before, generates ATP, and ATP releases insulin. Now, this guy, hexokinase, is extrahepatic. So for example, muscle cells have hexokinase. How does the glucose get into a muscle cell? GLUT4. GLUT4 has a low Km. Hexokinase has a low Km. Okay, so again, there's that pairing to make kind of a metabolic, appropriate response metabolically. So muscle cells won't, once they phosphorylate glucose, they'll basically trap it. They won't put it back into the blood. So it's not really a good scenario for tissues other than muscle that need glucose. So we'll kind of come back to that. That's the first time I've said that, and then we'll go to some other graphs that I'll go through that again and kind of show you how it works. Okay, so far that's just in your notes. Yep.
So once the glucose is phosphorylated in liver, what cleaves the phosphate to let it go out?
We haven't said that yet. Yeah, there's another enzyme. Yep, because you're right. To go backwards, there's a different enzyme.
What happens when like all the glycogen that was on reserve in the liver is like used? If there's like starvation happening or something, like the brain uses like ketones, what does the blood use?
Well, so the liver will, in that case, will try to optimize gluconeogenesis. That's kind of something that's always running, but in certain conditions like that, gluconeogenesis goes up significantly. So that's a great point that kind of goes into the next slide. Yep. Okay, so we'll kind of come back to that. So far, just a couple pieces there. So we're going to talk about a cycle called the Cori Cycle. Have you heard of that? Okay. So the Cori Cycle is relevant for us because it is it's an ongoing cycle that is a significant process in glucose metabolism, and I'll show you why. So the cycle provides a metabolic connection between the liver and other tissues that depend on glucose for energy. And examples of tissues involved include red blood cells and muscle tissue. So if we look at this diagram, we can use this basic diagram. We can modify this a little bit by putting muscle cell here too. So red blood cell and muscle cells are two of the most important tissues in this process. So let's start in the blood there with glucose right in the middle. And in this case, it's showing glucose going into red blood cells. And remember, red blood cells take glucose, run glycolysis, so it converts it to pyruvate. And then red blood cells go pyruvate to lactate. And then lactate runs down its concentration gradient out of the red blood cells into the blood. Several tissues take up the lactate, but especially the liver. And I'll tell you why. The liver can do this. It can go lactate to pyruvate and then to glucose. So here's gluconeogenesis. Remember, the liver is really the main tissue that does gluconeogenesis. It does at least 90% of it. So the liver can take the lactate, convert it to glucose, and put the glucose back into the blood. That same glucose molecule could keep doing this. Right? If you track the carbons, have you done that in any other classes? Let's say we label this carbon. I remember as an undergrad, I thought, I don't get it. And then the first experiment I did as a grad student, we tracked carbons for research, and I went, oh, okay, that's kind of helpful. But if you thought about that, then basically it's recycling. It's going through this process. Now, muscles can also do that. They'll take glucose, go to pyruvate, they'll go glycolysis, and then make lactate. Muscles don't always do that, though. They'll do that during what type of exercise? Yeah, anaerobic exercise. They'll run that. Aerobic conditions, it's minimal lactate production. But there's always some lactate in your blood. I think a lot of people think, oh, it's just during exercise. But there's always a little bit. Why? Red blood cells. They're always doing that. The reason there's not more is because tissues like the liver take the lactate and convert it back. Here's why it's so important for us. It's estimated that approximately 40% of glucose in the blood is involved in the Cori cycle. It's estimated that 40% of the glucose in the blood is part of the Cori cycle. That's pretty significant. Is gluconeogenesis always occurring? Yes. But it's increased during times of like starvation and fasting. So gluconeogenesis is ongoing, but it's increased during fasting and starvation. And kind of a simple, like how would you, if you had to put a time frame on this, what's kind of the difference here? Like how many hours or days or weeks is kind of typically used? Have you ever talked about this? Apparently not. What do you think? Like a lot of times we'll go, oh man, I need 3 hours, I'm starving. That's commonly used as the cutoff. Why? Does that time frame ring a bell?
The hepatic glycogen stores.
Hepatic glycogenolysis is basically depleted liver glycogen. As soon as that happens, metabolism shifts into kind of a starvation phase. So we lose that glycogen, and now as we go this way, what's happening to gluconeogenesis? It's accelerated, because now it's the only game in town. No more glycogen, liver accentuates gluconeogenesis. But gluconeogenesis is always occurring because of the Cori cycle, but it goes up and down. Okay. One more question about this. Is Cori cycle an effective way to increase blood glucose? Is the Cori cycle an effective way to increase the concentration of blood glucose? Who says yes? Who says no? It was 6-2, I think. Okay. No, because it's not. There's not a net increase.
It's recycling.
Yeah, it's recycling. Yeah. So it's not increasing blood glucose, it's helping maintain it. So that's one of the points of it. But this is a good example of how tissues kind of cooperate metabolically. The liver can do gluconeogenesis, other tissues can't. The liver, though, can burn fat, but a lot of other cells can't. Red blood cells can't. So the liver can get a lot of energy from fat. It can take some of that energy from the fat, get ATP, and use that to make glucose for other tissues. So this is kind of metabolic cooperation between tissues. And you can look at it the same way with muscle, red blood cells, brain and central nervous system. The liver's helping support them by gluconeogenesis. Okay? Good there? So let's go to the next one. Let's talk about hormonal regulation. That's a few ways that we regulate blood glucose metabolically using transporters and kinases in the Cori cycle. The hormones, Dr. Adams went through a little bit. I'll add a little bit to this. These are the major hormones that we're going to talk about, insulin, glucagon, and epinephrine. And there's others involved, but we know insulin decreases blood glucose. Glucagon increases blood glucose. Epinephrine, what's another name for epinephrine? Adrenaline. What do you think, increase or decrease blood glucose? Increase. Which tissue makes epinephrine? Adrenal glands, or adrenaline, adrenal glands. So what stimulates the release of epinephrine? So along the same track, let's say one word. Stress. physical, emotional stress. Okay? Epinephrine is mostly stimulated by physical activity. So the person starts being physically active, epinephrine levels in the blood start to go up. So epinephrine, one of its main functions, provide energy. In the form of either glucose or fat. So in a few weeks, we'll talk about burning fat, and we'll come back to epinephrine in that case. Now we'll talk about glucagon. Okay, we're going to focus on insulin and glucagon, and the first one is just this is an old diagram from a classic text called the Guyton text, which are basically artwork involving things like this. This diagram shows a part of the pancreas known as the islets of Langerhans. You guys have probably all heard of that. They are structures that are hormonal. When we talked about pancreas, we said about 2% of the pancreas is endocrine function. And that includes a few different cell types, alpha cells and beta cells. So the alpha cells release glucagon. Alpha cells release glucagon. Beta cells release insulin. Well, they're right next to each other. So they're exposed to the same conditions. So when blood glucose goes up, insulin's released. When blood glucose drops, insulin secretion goes down, glucagon goes up. It makes sense to have them in the same tissue, and they're right adjacent to each other that can release different hormones. And then the hormones travel through the blood. They're both peptides, so whichever cells have their receptors, that can cause a hormone-specific response. Okay? Insulin doesn't just affect blood glucose. It's an anabolic hormone. It's actually one of the most important anabolic hormones we have, and we can kind of control its release. So in other words, I've mentioned a couple times in here, if a person exercises, sometimes it's advantageous to have carbohydrate after the exercise. One of the reasons it stimulates insulin release. So insulin helps store glucose, but it also helps do things like increase protein synthesis, decrease protein degradation, because it's anabolic. And that can help, for example, muscle tissue recover. So just think of insulin in general as a very potent anabolic hormone. So anytime I say, hey, which hormone do you think makes cholesterol? You're going to say, insulin. Which hormone do you think makes this? Insulin. Okay? So this is what normally happens. Yep.
So that's why having a carbohydrate source after exercise is good for building muscle.
It can be, yeah. That's one of the reasons, because it tends to stimulate the release of insulin. Insulin is anabolic, helps make glycogen, helps muscle proteins be synthesized, and can help the repair process. Yep. So it's kind of both. So let's look at an experiment on how this goes. So this is just showing, this is another one where we could say, okay, be careful what you volunteer or sign up for. These individuals in this test did a fast. They did a 4-day fast. Before they started their fast, they measured blood glucose, which is up at the top, open circles. You can see at the beginning of the fast it was about 90. Remember we said insulin tends to stay between 90 and 110 mg per deciliter. Okay? Now, at that point, that's a relatively moderate amount of glucose, so insulin is relatively low. So if we look at this point, here's our insulin value, and here's glucagon. Now, as they continue to kind of fast over this or go into starvation mode, blood glucose drops a little bit more, starts going down. Why doesn't the glucose continue to go down to 10 or 0 or... Because glucagon's released. So blood glucose is dropping, insulin is depressed, but glucagon's released. And glucagon is stimulating hepatic glycogenolysis. And what other process to increase blood glucose? Gluconeogenesis. Glucagon stimulates hepatic glycogenolysis and gluconeogenesis. Glucagon stimulates hepatic glycogenolysis and gluconeogenesis. Okay, so that's kind of what happens consistently. Blood glucose goes up, it changes the hormones. It goes down, it changes the hormones. So typically those hormones kind of balance each other and affect and regulate blood glucose. That's typically what should happen. Last time we talked a little bit about, Dr. Adams talked about diabetes, the different types, type 1 and type 2. Remember, type 1 is, we call insulin dependent, typically. And there's reasons why the nomenclature's changed. I won't go into all that. But now we basically refer to this as type 1. And in that case, it's where the individual is typically not making adequate amounts of insulin. So they can inject insulin, and it works. In this case, remember, type 1, their beta cells have been depleted because of an autoimmune response. What does that mean? Autoimmune. Yeah, that means your immune system recognizes a part of the beta cells as harmful and actually kind of destroys its own beta cells. And now the insulin is no longer made. When they inject insulin, insulin does what it should in the tissues. Okay, type 2 is different. Type 2 is non-insulin dependent. Although some type 2s take insulin and it works. So that's why we tend to say it's type 2. But type 2 basically involves insulin resistance. And if you remember from what he talked about, there is typically kind of a progression of events that eventually culminate in type 2. And initially what happens is, in the initial stages of type 2, tissues become insulin resistant. We talked about this a little bit already, right? Essentially, we lose this. Say this is a cell's insulin receptors. Let's say this is insulin. And typically we get this signal cascade. In type 2, what happens is, even though the insulin is made, tissues don't respond to it the way they should, and you start getting a decrease in this insulin signaling. Now, unfortunately, what that means is, let's say this is GLUT4. That can mean that this response is slowed, so that now glucose stays in the blood. So in the initial stages of insulin resistance, it's high insulin, high glucose. And we call that, remember what he said? It's not diabetes yet, it's pre-diabetes. So in pre-diabetes, in general, high insulin, high blood glucose. Something along the signal cascade has now compromised the ability of GLUT4 to absorb glucose from the blood, so blood glucose stays high. What do the beta cells do? They respond by making more insulin. So insulin stays high, blood glucose stays high. Remember, this is where we said, a lot of times people will say, oh, we don't even measure insulin because we know what's coming. I think it is valuable to measure insulin. It can be an indicator. And then diabetes. So we're going to say this is type 2. Diabetes is what? What happens to the insulin? So we know this can be high blood glucose What happens to the insulin, high or low? After a period of time, the beta cells can be damaged by that high glucose. There's different terms for that. But most of the time, the insulin is low at that point. As soon as the insulin is low, then it's considered, oh, that's type 2 diabetes. Can it be reversed here?
Yes.
Sometimes, yeah. Not everyone with prediabetes develops diabetes, but a lot of them do. Can it be reversed? A lot of times it can. Change lifestyle, change diet, change exercise, do things like that can decrease the risk. A lot of times those, especially the muscle, can be stimulated to become more insulin sensitive. And that helps regulate blood glucose, and that can spare the beta cells. Even in this case, in type 2, sometimes you can have significant improvements in regulating blood glucose because of that. The point of it is, even if you have type 2 diabetes, if you control it, you have a healthy lifestyle, and you control it by exercise and diet and everything, you can minimize the effects of it. But it is, you should monitor blood glucose. I have family members that have type 2. Some of them monitor blood glucose, some of them don't. It's obviously a lot better when they do.
Is that initial insulin resistance caused by the system being overwhelmed by a lot of glucose?
No, it's the reason obesity is one of the risk factors is because especially did he mention anything about waist circumference? I don't think he really did. One of the reasons there's a strong correlation between waist circumference and the risk of type 2 diabetes is when we have fat cells basically their major function is to store fat and then release it when we need to. When we do that appropriately, we say, hey, we have metabolic flexibility. I think I've mentioned this before. If I can burn fat when I need to, then my metabolism is flexible. As we accumulate adipose tissue, those fat cells become abnormal. They tend to get too large. They tend to be have reduced vascularity. They become oxygen compromised. That stimulates inflammation, and then the fat cells start releasing molecules into the blood that are a problem. So this process can come from things like this. And we can call things like adipokines. Have you ever heard that term? So let's say this is a fat cell. Fat cells, when they get too large and become dysfunctional, can release molecules into the blood. Some of those molecules, let's say this is a muscle cell, they can release molecules into the blood that either bind receptors on the fat cells or actually enter the fat cell, and they're the ones that do that. So that's where you get this kind of crosstalk between tissues that's harmful. So that's one of the things that can cause that. And there's quite a few other things. There's a lot of proteins involved here. Anytime you have a protein involved, there's genes involved. So is there a genetic predisposition to risk of type 2 diabetes? There is. There is a genetic component to this as well. But we all have kind of, I don't know how you'd say it, kind of genetic windows. Like I have elevated risk for certain things. If I modify my diet and lifestyle, though, I can kind of minimize risk as well. So you can have a genetic predisposition for something, but still keep your risk low. It's like heart disease. It's multifactorial. As long as I kind of control things, like some people say, oh, I have high cholesterol. I'm probably going to have heart disease. It's also blood pressure. Do you smoke? It's a lot of other things. So I try to control all the things that I can and do that to minimize my genetic predisposition. So it doesn't mean that it's going to happen. It means that you just have elevated risk for something. You've probably talked about that before in other classes, right? So there's a few things that are involved in that, but that's generally what happens. And this is kind of what this summarizes. The beta cells actually sense elevated blood glucose. They release insulin. That allows glucose to go into cells. And it's kind of a nice system when it's working, right? Because One tissue is basically sensing it and then releasing molecules to allow that blood glucose to go into other tissues. And GLUT4 is most likely involved in most of the time in type 2 diabetes. So this is a diagram that shows that. So at the top we have kind of what typically happens. So in this case we have basal levels of insulin in this case. We have GLUT4 being made from the GLUT4 gene. It's being transcribed, and then here's translation. It's translated. And GLUT4, remember, goes through the secretory pathway. So in this case, it's been inserted in the membranes of Golgi, and these are waiting for insulin. And now insulin is released. It goes up in the blood, stimulates its receptor, and now it causes these GLUT4-containing vesicles to move to the plasma membrane, embed, and allow glucose to go in. We've talked about this before. So what kind of cell is this? Looks good. Looks good. I don't know what kind of cell. What do you think? What's a tip? GLUT4. Likely a muscle cell. Could be a fat cell. But the most important tissue for regulating glucose peripherally is muscle. So remember this 30, 40 years order down the road, go, oh yeah, Reeve said muscle's an issue. So it's important as we get older, we try to maintain muscle tissue because it helps regulate blood glucose. Okay? And if we look down here, let's say an insulin deficiency. So this could be starvation, or in diabetes when insulin is low. Insulin actually increases expression of the GLUT4 gene. So you end up with less transcription. So you have less protein, and you have a decreased insulin response. And so you have a lot less GLUT4, so glucose stays in the blood. Okay? In clinical nutrition, you'll talk about medications related to all of this, type 1 and type 2, and you'll see the different varieties. But and again, probably, what's the percent of individuals in the U.S. if they're diabetic, it's type 1 or type 2? About 90 to 95% of cases of diabetes tend to be type 2. Right, used to be more common. Age is another risk factor, but obviously now there's so many kids with type 2 diabetes that we no longer call it adult onset. But the numbers are really a problem. I think in the U.S. there's about 100 million pre-diabetics. Is that a lot? How many people live in California? Any idea? 38, 39 million probably. So is that a lot of pre-diabetes in the U.S.? There's probably 320 million people in the U.S. Probably 25 to 30% of people living in the U.S. pre-diabetic. A lot of them don't know. It's very important. And I think I've said this before in life. There's important things you want to know. What's your favorite color? What's your favorite song? What's your fasting blood glucose? What are your blood lipid values? What's your bone density? All kinds of things like that. Most people have no idea what their fasting blood glucose value is. How many of you guys have had that done? Okay. 3 or 4 of us. Okay. Encourage your parents, your friends, all those individuals. They should know their fasting blood glucose. Everyone should do it periodically. Okay. It's the end of my nagging session. We good there? Okay. I mean, nutrition is such an interesting field for a lot of different reasons, but hopefully people will continue to and with technology, we should be able to improve kind of the markers that we're looking for to improve our health. And then we should be able to use nutrition in a lot of different ways to either prevent or improve a person's health. I'm actually going to stop it there. It's probably a good stopping point. I'm going to try to stop it here.